Hello, everyone, and thank you for joining us for today's webinar. My name is Kaylin Shores, and I'll be moderating today's presentation on 2021 R2 EMA3D Cable, faster EMC solving for electronic devices and entire vehicles. Before we start the presentation, let's review the user interface. On the top of your screen, you will see a bar with 4 options for you to click. To ask questions, please click and open the Show Conversation option. This will show the meeting chat, and this is where you may ask any questions you have during the presentation. At any time during the presentation, you can submit your question. Your question will be placed in a queue and will be addressed at the end of the presentation. Any questions left unanswered will be responded to via email. All right, on to today's speaker. Tim McDonald is president of Electromagnetic Applications, where he has implemented new system modeling approaches to simulate the interaction of systems and their electronics with electromagnetic environments in a shorter time, with more accuracy, and at a lower cost. He is a consultant to NASA DoD major primes for specialty engineering of critical systems, development of novel material solutions, and EMI/EMC problems, and in the execution of major programs that require verification to electromagnetic environmental effects. Without further delay, I'll pass it off to Tim to get us started.
Thank you very much, Kaylin. So today we're going to talk about advances in EMA3D cable for EMC design for both devices and vehicles. So let's talk about what the EMC design process life cycle looks like. So we start with the actual design of the electronics unit itself. Generally, these days, that's very quickly followed by an electromagnetic simulation step to assess the performance of the device. So that may be done at the PCB or board level, at the enclosure level, subsystem level, or the vehicle level. Then at the end of that simulation step, engineers can assess if there's any problems and then apply mitigations to hopefully solve any problems. The next step is fabrication of the EMC device, the prototype that will be used for testing. Then that test unit will typically go into an EMC chamber. Depending on the industry and the contractual obligations, it will be tested in the chamber for compliance. And then once all of that testing is done and the other device testing and development processes are done, you enter device production. So the first 3 phases, those are the times that you want to find or anticipate EMC problems. The last 3 phases, it gets harder and more expensive and riskier to have EMC problems. So this chart essentially describes the previous approach to EMC. So we design, build, and test units, and there's no simulation step. If you find a problem during this phase, it can be very expensive as you're scaling up production to make a change. However, making changes in the design of our product early is very inexpensive, but you can't really do that with the previous approach. You can use best practices, but without simulation, you don't have the ability to predict the performance. So adding simulation can decrease cost because we're making changes at a point in the program when it's less expensive to do so. It certainly decreases risk going into EMC testing, risk that we may have a schedule delay or a costly design mitigation. Today, I'm mostly going to be talking about EMA3D Cable. EMA3D Cable is a product that is developed by EMA. It is sold worldwide exclusively through ANSYS. So please contact an ANSYS or ANSYS channel partner sales associate if you have interest in getting access to the product, EMA3D Cable. Let's talk about some of the requirements that we can address in the domain of EMC with EMA3D Cable. Radiated immunity, where we're looking at how fields can affect the performance of a device from external from that device. Radiated emissions, this is when devices emit unintentional energy, and that energy may be beyond a limit that is imposed to keep it from interfering with other devices. Electrostatic discharge, we all know when we touch a device, it is possible that we can have a little static discharge. Those ESD events can be disruptive to the performance of devices. And so there may be performance requirements or safety requirements for ESD control and mitigation. Conducted emissions, this is mostly on power lines, essentially limiting the amount of unintentional interference that can be emitted from a device onto the power line. Conducted immunity, these are making sure that devices can handle a level of unintentional noise on the power line besides the power itself. EMA3D cable can be very helpful for signal integrity and power integrity, especially when we have to take the cables and enclosure into account. And finally, it's a very helpful tool for other types of EMC metrics like transfer impedance. And we'll talk about that a little bit more. So the question is, why EMA3D cable? So likely everyone knows that there are existing simulation tools for board level simulation. The ECAD can be imported. Circuits can be modeled with simulated bits and clocks, and you can capture the emissions from a board. The issue is that the units that are tested for EMC are not bare boards in free space. EMC coupling is heavily impacted by things like cables and enclosures. We have shields potentially around cables. We have connectors, terminations of those connectors. We have apertures in the enclosure, like holes for venting, holes for fans. We have a seam and joint at lids. Those seams may be gasketed. They may be circuitous path. It may be just a direct, simple interface at those lids. And then we may have some very complex frequency-dependent materials like EMI absorbing tapes or cable chokes. So existing simulation methods are very heavily optimized for board EMC, but they become prohibitively challenging and expensive to do to consider all the other enclosure and cable effects that I mentioned above. EMA3D cable is a solution to these challenges. So the distinguishing features here, we have been using EMA3D cable for electronics and platforms for many decades, since 1978. It is a full wave solver of Maxwell's equation, so it's a very accurate method with the fewest approximations of any method. And it is fully co-simulated with a wire harness solver, something like transmission line theory for the wire harness solver, but it's actually heavily modified, so it's better described as a wire simulation code. The product is integrated within the ANSYS space claim interface and will soon be the ANSYS discovery interface. It's very intuitive for new users. We utilize mechanical CAD heavily. So that's the biggest difference. The enclosure, the cables, they're not in ECAD. They're in the mechanical CAD. And dealing with cleaning and preparing that mechanical CAD for simulation can be very time-consuming and cumbersome. The EMA3D cable, because it has a very forgiving voxel-style mesh, allows us to import the mechanical CAD and define models for the cables in a fraction of the man-hours of other methods. And our workflow for EMA3D cable is integrated with ANSYS SI-Wave and ANSYS HFSS, so we can take advantage of the tools that are optimized to work with boards. So let's talk about some of those individual EMC environments that I mentioned before. Let's first talk about electrostatic discharge. Generally, as a designer, you're trying to make sure that your device meets its performance requirements when exposed to the ESD environment, whether that might be an ESD gun test or another type of metric. We want to find those issues where we could be susceptible to upset or damage from ESD. And we want to be able to do that before we have a physical prototype. And we want to be able to deliver ESD compliant products without having to over-design it. That could also be a problem. We could follow EMC best practices, but we could overdo it and make our device more expensive than it needs to be. With the EMA3D cable, we've got the ability to do a time domain full wave solution, which is certainly advantageous for ESD because ESD is best posed as a transient problem. We can co-simulate the 3D solver with our wire harness simulation. And with that, we can consider things that are much smaller than our computational mesh, like the tiny strands within a braided shield, really thin foils in a cable shield, or other types of small conductors. And again, as I mentioned before, the workflow here is very rapid, and it basically uses the mechanical CAD with very little simplification so that we can go from mechanical CAD import to actually getting a simulation in the shortest period of time. The benefit is we end up with a product that is cost optimized and compliant with the least amount of risk going into ESD testing. So we're reducing the engineering cost and risk and getting products to market faster. Okay, let's talk a little bit about radiated emissions product design, and then I'm going to go into some detailed modeling cases for those items pictured on this page. So our goal with radiated emissions is, again, we want to meet our regulatory or our contractual performance limits. We want to find the problems that are causing radiated emissions failures. That could be at the PCB level. We could have a bad design at the board. It could be that the board is okay, but the enclosure is the place where the design is suboptimal. It could be the cables. In fact, often is the cables. A poor grounding scheme. It could be bonding or the materials that we're using in our device design. We want to be able to get an EMC compliant product for radiated emissions in the shortest possible time. A nice thing about our tool is we can pull in the near field emissions from SI wave and HFSS, or even from experimental approaches like near field scans. And what this allows us to do is let those near field scans or those other tools for PCBs do what they do best, and we can use EMA3D cable for the cables and enclosures. Again, with the EMA3D cable, we co-simulate with a wire harness simulation code, so we can consider all those small details, and it's a really fast workflow. And I'll show that in just a moment. Again, our goal here is cost optimized product so that we're doing all this engineering before we have a prototype, and we're making our design changes when it's least costly. Okay, let's talk about an example, what this workflow looks like. So let's start just a quick introduction to ANSYS SI Wave. It's a tool that has many types of solvers built into it so that we can deal with boards and simulate many aspects of the compliance of that board, not just EMC, but for today, we're going to be talking about the radiated emissions prediction of boards with SI Wave. So here's an example board in SI Wave. We've got one microprocessor, 2 memory chips, and then we're going to be analyzing multiple signal nets on this board. So the SI wave prediction it's incredibly computationally efficient, and we're getting the emissions at the board level here. Here we're showing 100 megahertz, but this was simulated across a pretty wide range of frequencies. EMA3D cable lets us pull in those SI wave near fields from the board incredibly quickly. It's a one-step process. We click import fields, we navigate to the SI wave fields, and then the final step is we just have to translate and rotate that into position. And you can see the arrows in the user interface. They make it very easy to move the board into the right location. We're not limited to just one board. We can have multiple boards in our simulation. There's no limit to the number. Then we can specify our seams in our enclosure. In this case, we're highlighting our seam joint tool. So rather than having to closely sub-model this interface, take a look at the gasket, we can simply specify the seam resistance, capacitance, and inductance, which allows us to specify a seam in about 10 seconds, the time it takes to click the lines around that interface. As I mentioned before, EMA3D cable has a very forgiving voxel style mesh. You can see the small cubes here so that we're working with the mechanical CAD. We don't have to do any geometry cleaning or preparation. And then to take a look at our radiated emissions, you can see the SI wave fields are being captured in the center of this enclosure. Those fields build up inside the enclosure, and then they radiate through the seam outside the box. And our observation location is some distance away from the unit outside the box. This just shows the side view of the same thing. We can see the fields on this plane. You can see we have reasonably high fields inside the box, and then several dB down, we see the fields outside the box at our observation location. And it's that observation location where we will capture the fields versus frequency to compare to our radiated emissions limit. So for an example, this shows the fields inside the enclosure. You can see we're at about 3 millivolts per meter, and we're capturing this at each frequency. One advantage of EMA3D is we get all very tight frequency spacing, and we get a broad range of frequencies in one simulation. This is a single simulation run. Outside the enclosure, you can see we're about a 0.5 millivolt per meter. There's some about 20 dB of shielding effectiveness that we're observing, and the effects of the seam are shown as different frequencies are able to get outside the box compared to what's inside the box. So all of this post-processing is done automatically in EMA3D cable for the user. Okay, let's talk about a different type of device. In this case, we're looking at a consumer cell phone, and that cell phone has two features. One, it has a power cable. The power cable is designed with power and signal cables, and then we have a board in SI wave, and then we capture the near fields and translate that into position in the cell phone. And again, on the edge of the cell phone, we define a seam. So again, you can see the board radiating. We can see that radiation escape the seams in the phone. Separate, we can see the pulse from the cable itself. And so the radiated emission some distance away from the phone is a combination of the emissions from the board that escape the phone through the seams and the emissions that come from the cable. So it's really giving us a prediction way beyond what you get just at the board level. It's helping us do a holistic product evaluation for its emissions. And it's easy step-by-step process, does not take many man hours to perform, and it's actually a very easy tool to learn. Okay, let's talk about the use of EMA3D cable for cable and connector signal and power integrity analysis. So again, we need to design cables and connectors that meet the contractual performance requirements. We want to find design features that degrade the performance of for signal metrics or power quality metrics. And we want to be able to analyze that further in other tools. So we want to be able to take a scattering matrix parameter characterization or S parameter characterization. For us, what that means is we calculate the ports for the S parameters and create a touchstone file. And that touchstone file is created for the user automatically when we run the tool. And that S parameter characterization can be wired up in a circuit solver. Really, in almost any circuit solver can handle touchstone file import, and you can wire it up and do further analysis for signal and power integrity. And so we have the ability to model things like the twisting of cables, skin effects, complex harness geometries. There's really no limit to the number of shields and the type of geometry that we can deal with, because we're hybridized between an arbitrary 3D geometry and the ability to model transmission lines. So if something doesn't fit the transmission line paradigm, we can model it in 3D. In cases where it does make sense to use the transmission line, we can greatly reduce our simulation time. And again, we're able to be a little bit less man effort in preparing for simulation, we can import the CAD for the connectors. We can quickly specify the cross-section of the cables and determine our performance specifications. Now, we talked a little bit ago about radiated emissions. The corollary of that, or the close cousin of that, is radiated immunity or radiated susceptibility. In this case, the field comes external from the device, and we're looking how it impacts the product itself. Typically, you take the device into an anechoic chamber or a reverberant chamber, apply an external source, and then monitor the health or the operational performance of the device to see if it is upset or potentially damaged. Now, in this case, it is not always as easy to use a board-based simulation tool, which are not necessarily set up to consider the type of reverberant source or the source that you might see for a device inside of an enclosure. So EMA3D Cable has the ability to create a region of the model where we can create a subgrid. And that subgrid can be used to model things like PCB planes, vias, traces, ground planes with a very high resolution and a very small mesh size. We can then model the rest of the enclosure and the cable with a much larger computational mesh. And what this allows us to do is combine those two into a single evaluation that considers both scales of the problem at the same time. And what this means is we can consider the shielding effects of the enclosure. We've got that very easy tool that allows us to quickly specify seams based on seam impedance. We've got the coupling into the enclosure and to the PCB from the cables. But then when it is time to look at the PCB itself, we can look at the planes directly with the subgrid, and we can estimate the induced voltages at the critical interfaces for downstream evaluation. Okay, let's talk a little bit about transfer impedance. Transfer impedance is a very popular method, and it's becoming standard in many electromagnetic disciplines for consideration of the shielding effects of cables and connectors. And the advantage is apparent when we consider the fact that shielding effectiveness is not an intrinsic property. If you tell me the shielding effectiveness, for example, of a cable, that the answer of that will change in how I do that measurement. However, if we do a transfer impedance measurement the right way, it's an intrinsic property of the cable and connector. So you can change the measurement approach, but you generally should get the same answer. So in some cases, transfer impedance is, if you're a designer of cables and connectors, it may be your contractual obligation to meet a certain transfer impedance. In other cases, you are an integrator of systems and you simply want to use transfer impedance as a method to quickly understand the coupling of electromagnetic energy to your platform. So again, we want to be able to predict transfer impedance and also to use transfer impedance. When we're predicting transfer impedance, EMA3D Cable lets us model the connectors in 3D. It lets us model the cable cross-section using our transmission line theory, where that's possible with cables, and combine the two into one single simulation, and we can be predictive of transfer impedance. But we can flip that around as well. Our product allows us to use transfer impedance of connectors and cables as an input to the product. So once we know what it is from a submodel or from a measurement or from both, we can use those as inputs to EMA3D. And that lets us do full platform modeling at reduced analyst effort, but with still retaining very high accuracy across a wide range of frequencies. So if you're a company, if your group uses transfer impedance as an important metric, either as a design goal or as a step to understanding your platform coupling, EMA3D Cable is the right tool for you because we use the same paradigm. Okay, let's talk about conducted emissions and conducted immunity. So to do CE, CS, or CI, we generally care quite a lot about circuit modeling of the power system. A challenge is that that model is very sensitive to stray capacitance and to the inductance of the power line itself. So in the past, engineers just had to use hand calculations or do their best for the transmission line of the cable. However, EMA3D cable lets us create very accurate simulations of the cables themselves and extract, as we mentioned before, we can extract the touchstone characterization of the cables, and that will have built into it the crosstalk between conductors, the stray capacitance, as well as the inductance of those individual cables. It's a frequency dependent characterization. It can be dropped directly into the CECS analyses. So this can solve a big problem. And we can consider more than just the cable. The cable can be solved for its S parameters in the presence of the 3D geometry. So you can have a cable routed through an automobile, cable routed through an aircraft, a cable in an electronics device, and all the effects of that capacitance to the nearby metal structures of those vehicles or devices is considered when EMA3D does the S parameter characterization. So it can be very accurate and consider all those side effects. But their true advantage is really just the amount of time it takes to build that model. Because we can import the mechanical CAD, we're able to do these analyses at a fraction of the time of competitors. Okay, we've talked a lot about electronic devices. Let's look at slightly bigger devices. Let's take a look at automotive and industrial platforms. So let's get started. Let's talk about vehicle electronics. So in the past, we only had to consider EMI/EMC as a regulatory requirement for a very small number of systems in the vehicle. The reason is we only have regulatory requirements for safety critical parts of the car. In the past, there weren't that many safety critical parts of an automobile. The ignition, the braking system, anything that was mechanical and not electrical maybe did not need electromagnetic testing. But that's changed. Now we have radars that help us with lane keeping. We have an increasing level of autonomous features. It can take control of the steering wheel. We also have increasing electrification. So there's more items that are deemed safety critical. And because of electrification, we have a greater prevalence of high power, potentially noisy sources on the vehicle. So the challenges for electromagnetics in vehicles is really huge compared to what it used to be. So we have to pass complex EMC tests, international standards, as well as national government standards for safety, as well as just quality standards. So failure in the early designs phase can be a huge cost. For example, if you fail for a vehicle on a safety critical product at the full vehicle level, you can't sell your car, and it has to just come off the assembly line and be parked in a parking lot. So it's very important as our job gets harder that we include simulation in the design to de-risk and reduce the cost of the development process for EMC. And just like we said before, there's very good tools that exist for board level EMC, but we have to do better than that because our criteria for success is typically at the vehicle level. And so we have to consider the cables, we have to consider the structures, the cable shields, the metal frames, the battery packs. All of those need to be considered when we consider EMC. In the past, that might have been impossible. In fact, we've heard many people tell us that the work we do every day is not possible to do, but it is. And the reason is that we have the voxel-based meshes that are able to handle directly the mechanical CAD. And so that takes a lot of the man-hour effort out of developing these full vehicle models. So again, in vehicles, ESD is a critical requirement. If you have ESD, for example, to a touch panel in your car, that touch panel may now have a safety critical function. So that can be a big deal. Again, an important environment is radiated emissions from the vehicle. Again, we've got the ability to capture those fields from SI wave and then include those SI wave fields in the full vehicle simulation. And then also we can have radiated emissions from the cables. So we need to be able to consider the cable effects as well. So I'm going to talk about a concrete example. So let's take a look at this electric vehicle, and let's look at the cables that connect. So we've got high voltage batteries that are connecting to a motor. We've got DC-DC converters. We've got a low voltage system. And so we've got quite a bit of potential for high and fast changes of current that could produce emissions at a broad range. So EMA3D cable, even with the complexity of the vehicle structures, the battery packs, the motors, we're able to put this model together very quickly, mesh it in just minutes, and we can run this simulation that is predictive for 10 meters away from the vehicle based on the actual operation of the currents flowing through these cables. So you can see E field, this is the top view. You can actually see the cables themselves light up in red where the fields are the highest. And this plot is showing the current density. Obviously the current is mostly staying in the cables, but we're inducing some currents in the nearby structures. And then we can use the same model that we use for emissions for immunity. In this case, the source is outside the vehicle. And so we can look at the coupling to the cable system or to the electronic devices inside the car. We're using the same simulation model, we just have a different source. And this just takes minutes to set up. Again, this is the same, it's just a different view from the top of the vehicle. Okay, in full vehicles, we also have to consider signal integrity, power integrity. As I mentioned before, we can route those cables through an entire vehicle and extract the touchstone file. We can also take advantage of the subgrid. In this case, we can look at the cable close to the connector, but we can also include the details of the vehicle itself. Radiated immunity, we already saw an example of this. We can have multiple subgrids as needed to look at the electronics all the way down to the PCB level from the vehicle level. So these multi-scale type problems become more tractable. What might have been considered a research project or too long and expensive to be part of a production program are now possible and achievable. And as we talked about before, transfer impedance, the way that transfer impedance helps our program at the vehicle level is that it allows us to parameterize the transfer impedance through a submodel or measurement and apply that at the vehicle level so that it takes us less time to build the overall model. If we do one submodel for one style of connector, we can use the resulting transfer impedance metric over and over again without having to rerun that simulation in the full vehicle simulation. We can save ourselves time. And again, with the conducted emissions, conducted immunity, we can do this at the full vehicle level. We can import all the cables from KVL if users are using a harness database tool like Zuken E3. We can quickly import that cable harness for the whole vehicle all at once. And we can characterize the S parameters for all ports of that cable and use that for CECS analysis. Okay, let's talk about application of EMA3D cable in aerospace and defense. So we have many of the same challenges that we have in devices and vehicles, but we also have external electromagnetic effects. The electromagnetic environmental effects, or E3, are specified outside of the aircraft. So they're things like lightning, or for example, imagine an aircraft flies near a military radar, or it flies near an FM transmitter tower. That environment is called high intensity radiated fields, or it's the abbreviation HIRF is called HIRF. HIRF and lightning are very important environments, but a little bit different nature than other types of EMC environments. Unfortunately, the governments that certify aircraft don't make our life easy. They specify the HIRF and lightning environment external to the aircraft, but they leave it up to the certification process of the applicant to do the coupling of those external environments to the individual electronics interfaces. So what you see is just a picture from the open web for a lightning style verification test where you inject lightning current to a platform and you're looking at the induced voltage and current on the inside. The problem is that's too late in the program. By the time you have an aircraft coming off the assembly line, you've already designed for lightning and HIRF all of your cables and your equipment. You don't want a problem at that point. So we really need simulation in order to model lightning and HIRF early in a program so that we have basically no risk going into this testing because it's really too late to make a change at this point. Let's talk a little bit about lightning indirect effects. Again, we want to be able to assess our platform early in the program and quickly model it. And these models are hard, or they have been in the past, because it's not just the outside of the aircraft. We need to consider everywhere current can flow. We need all the bulkheads, interior structures, and all the cable harnesses. So we're talking about thousands of pieces of copper. How is that possible? Well, recent advances in tools, including EMA3D cable, make this reasonable. So we can import all of the CAD into EMA3D cable. And because of the forgiving mesh, we have limited requirements to simplify the mechanical CAD. And the harnesses can be specified quickly. They can be imported from KBL or other means. And we've shown that with the simulated lightning strike compared to an experimental measurement, we can get really great validation between the two within 6 dB. And so we've shown good correlation on dozens of programs. Here's one that was published in January of this year on an electric aircraft test program. You can see a mock-up of the cockpit with the electronics, and interior structures was fabricated and measured, and there was good correlation between that and a full cockpit simulation. Recently, this plot was approved for public release. This is from cooperation with the US Navy, the NAVAIR division. An aircraft was simulated and measured for lightning injection, and there was fantastic correlation between simulation and test for dozens of interfaces. So lightning, we can get an accurate result. HIRF, we can get an accurate result. For HIRF, let's talk about what this process looks like. So for testing, essentially we have antenna placed outside of the aircraft, and we measure the coupling of fields outside the aircraft to individual electronics bays inside the aircraft. Number two, we measure the induced current on the cable bundles themselves. And again, if the cable harnesses are designed in a KBL exportable format, like in a product like Zuken E3, we can make our life easier by importing those cables directly. We can click import to import the file, and then we get all of the cable bundles, their location, their cross-section, their shielding, etc. And then, of course, EMA3D cable can handle things like cable twisting, cable shielding, handle braided cables, foil shields, and many other types of cables. So you can see the external HIRF coupling impinges on the aircraft, and we can calculate the shielding effectiveness. And taking it a step further, EMA3D automatically post-processes the data to give us the field statistics and bandwidth averaging that match what is done in actual measurements. So you can compare apples to apples. Further, we can simulate the current induced on the cables themselves, which is another important metric for HIRF. Okay, for lightning, for Part 25 aircraft, which is transport category aircraft, most aircraft you would fly on as a passenger are transport category aircraft. After 1998, after the TWA 800 incident, there has been increased requirements to prevent fuel tank ignition. What this means is a transport category aircraft today, it's almost impossible to get certified without a full aircraft simulation. And so EMA and EMA3D have been at the forefront of the past few decades in helping airframers get certification of their products to fuel tank ignition. So it forces us to do many validations so that a lot of the techniques and tools to get good correlation with experiment were developed as part of this process. The result is that EMA3D cable is certainly by far the best in class workflow for this problem. Number one, it's accurate, but number two, it can handle all the complexity of a wing with the least amount of analyst effort to build an entire aircraft or an entire wing model in the shortest period of time, least cost. Okay, there's other environments, and we have to consider more than just the full aircraft. Typically, we're flowing those lightning and HIRF levels to the units. As well, the units have all the usual EMC requirements, radiated emissions, radiated susceptibility, etc. Those usually manifest itself for the tier 1 suppliers as either mil standard 461 requirement, which is a unit level requirement in aerospace for electronics suppliers, or DL160, which is a civilian set of requirements, many of which are electromagnetic in nature. So it's very similar to what we've talked about before, where we can model not just the boards, but we can also consider the enclosures and the cables in the workflow that's best in class. Okay, I'd like to talk just very briefly about an environment called radio frequency interference, or RFI, and aircraft level EMC. So whenever we have an aircraft or spacecraft, or really any platform, we have to carefully consider the compatibility of all the onboard RF transmitters and receivers. And individual RF systems can have their performance degraded. They can be jammed. In other words, even when the interference is out of band with that antenna, with that radio system. So it's very important to consider the out-of-band performance of those radios. There are very good tools for coupling, as well as evaluating that performance. However, those tools sometimes are hard to use in things like heavily resonant cavities, or in cases where the coupling mechanism is not directly to an antenna, but through a cable connected to the antenna port itself. So EMA3D cable can help fill in the gap for this particular problem in cases where you might have resonant cavities, or cases where the cable is the dominant coupling mechanism. So in this case, a typical best practice would be to measure the RF component performance. A separate group at EMA has a system called the Automated Radio Measurement System that can be used to measure very quickly the susceptibility of radios. Whether you do this or another method, it's very important to measure the susceptibility and the emissions of all of your radio systems. Then we need to understand coupling. That coupling may be through cables or cavities. So that's the first step of analysis. It may also be port to port on the antennas, in which case ANSYS HFSS using SBR plus may be the best method. And then once we have all of those coupling levels, we can synthesize all of that data and visualize all the paths for interference, considering intermods as well, using ANSYS RF option with EMIT. Okay, so just as a summary, EMA3D cable, this is a tool that's been heavily validated and verified over 40 years against measurement, so that engineers can trust the results. EMA3D cable, it's really about the workflow. It's a streamlined workflow in SpaceClaim. It feels like a modern CAD tool in SpaceClaim. We can import almost any CAD format, very quickly mesh it with minimal amounts of CAD simplification because of a very forgiving mesh. And that's really critical for both small devices to large devices. We take problems that would be a research project or maybe weeks or months to prepare and turn them into something that can be done in hours because we can work directly off the mechanical CAD in many cases. We can consider all sources, multiple sources, cables, PCBs, multiple subgrids all at once. We can include all the relevant enclosure details, either explicitly or through submodels. And we can, of course, include all the cables, including multiple shields, multiple junctions, multiple branches. We can do all that in a single model that models it broadband from low frequency to high frequency. And it uses HPC technology so that users that maybe have ANSYS HPC packs or pools can use the same packs or pools for EMA3D. So a broad class of problems across a broad range of industries, and is easy to learn, and is the best in class, the least amount of labor effort to build and use these models. So that's the end of this presentation, and I'm gonna go back to Kaylin, and we'll start working through some of the questions as we have time.
Thank you, Tim, for that informative webinar. And now we'll get to the questions that we received. I do want to remind everyone that on the top of your screen, you'll see the bar with 4 options to click. If you want to ask a question, you just click the Show Conversation button, and then you can ask away there. But I just wanted to start with Ted. He said, is Touchstone a separate application from EMA3D Cable?
No, Touchstone is a file format for S parameter characterization. So it is a file format that EMA3D can export. Any IBIS or SPICE style, I say any, but majority of commercially popular circuit modelers can import the Touchstone format, including ANSYS Electronics Desktop, but users may be familiar with other type of SPICE simulation tools that they're using and maybe have invested a lot in locally.
All right, and then also, Ted, the slides will be available after the presentation is over. The next question is, can Creo-based harness be easily input into EMA3D Cable?
Yes, so there are multiple ways using Creo that you can specify your harness. A popular way to use Creo is to consider the harness 3D path, where the harness is basically just a tube in Creo, and the user may have a cable database for the wire board information. A popular cable database software is Zucchini 3. There are some other competitors. And EMA3D Cable is able to import the Creo path of the cable and assign each cable segment with the wire board information from the KBL export from, say, a Zucchini 3. That's a very popular workflow. In other cases, the Creo may have more of the cable information in the CAD explicitly, which EMA3D can directly import. And in the last case, in some cases, some software can already synthesize the cable wire information and the 3D information in KBL. In those cases, you can actually import the KBL and have the 3D path and the wire board information all in one import. Obviously, that last example is the easiest because it just takes seconds to import even the most complex harness. So long story short, we can work with Creo and all the popular ways that people store cable data in Creo.
All right, next question is it possible to simulate full electronics enclosures and their PCBs with EMA3D Cable? If so, how long does it take to build such a model?
Sure. So we showed an example of the Galileo board earlier in this presentation, where SI wave was used to model the entire electronics package that included a processor, 2 RAM modules, as well as about 16 individual nets of that circuit. we have a step-by-step guidance for the Galileo model. The SI wave portion takes maybe 20 minutes, including simulation time, and then the EMA3D portion takes another 10 minutes to set up the model and maybe an hour or two to simulate. So a new user can go through that process, and in half a day, they can be proficient on how to get the combination of SI wave and EMA3D.
All right, next question is from Jacob. What is a typical simulation run time on a standard desktop versus a workstation?
Yeah, so it depends what is being simulated and what resolution. Individual cable harnesses that are using a transmission line theory might resolve in seconds. Enclosures for shielding effectiveness might be just a few minutes. An entire enclosure with all the details meshed at 1 millimeter resolution might take a few hours. An entire aircraft at 25 millimeter resolution, which is typically what we do for Lightning and some parts of HIRF, that might take about 10 hours on an engineering workstation. EMA3D can run across clusters with hundreds of nodes. So if you really want to push to a high frequency, extremely high frequency, or extremely high geometric resolution, that is possible. And that the method that we use scales pretty well with the number of cores, high efficiency, in many cases higher than 75% scaling efficiency.
All right, next question is from Vandana. Can EMA3D cable be imported as a part of ANSYS Workbench?
Yes, so ANSYS Workbench is based also on compatibility with the SpaceClaim platform. So because our tool is 100% in SpaceClaim, anytime you can get geometry in SpaceClaim, you're in EMA3D. So there's very high compatibility with the ANSYS Workbench workflow. No loss of data, and actually no import needed because we're already in that data representation.
Okay, next question is from Sean. How scalable is the voxel mesh for small details on a large model?
Yeah, so there's many ways to handle that. So you can have an entire aircraft where we have extremely small voxels, and that is computationally expensive and may require a multi-core cluster. We have the ability to use the subgrids, so we can zoom in on some small parts of the aircraft, mesh them to a higher resolution, and combine them in an aircraft model that's more coarsely meshed. And those two representations are linked using Huygens currents. So there are some techniques that can take those computationally expensive problems and through the Huygens approximation, make them a little bit more computationally accessible. So it depends on what your needs are and whether you want the first cluster style simulation with many voxels, or if the Huygens approximation is appropriate for what you're simulating.
All right, next question. How has EMA3D cable been validated for EMC?
Yes, so we showed a few of the validations on the full aircraft platforms earlier, where we showed injection of current or illumination of field outside the aircraft, and we're validating that to field and current measurements to the inside. Because those are very high profile measurements, not all of them, actually the minority of them, but a few of them have been published in the open literature, so you can read about them. For individual electronics, we have full electronics validations. We've also have many cases where we've validated things like coupling through cable shields, cable crosstalk, validated them against measurements, and validated them against other simulation techniques. Just a quick note, FDTD is historically been a simulation technique that, because it has the fewest number of approximations, it's actually commonly used to validate other simulation techniques. So if you're looking for a very accurate and robust method that can handle complex geometry, FDTD is not a bad choice.
All right, it is time to conclude this session. As a reminder, any questions that we didn't get to will be addressed via email. You will also be receiving an email from us tomorrow with a link to the recording of this presentation as well as the slides. If you have any questions about a particular section, please feel free to reach out through EMA3D.com website or our email. Thank you for your time and attention and have a great rest of your day.